Okay, so we're back on the second clip now. So this capacitor here is what we call an electrolytic capacitor. The main difference with an electrolytic capacitor is it's polarized, so it has to be connected the right way round, otherwise it can start to bubble and squeak and you can destroy the capacitor. So I have to make sure when I'm connecting it, the positive is on the positive side and the negative here is on the negative side. So I need to connect that in like that. And I can start to charge the capacitor, and it charges very, very quickly, as it's explained in the video. Now, to discharge the capacitor, I can discharge it quickly by simply shorting it out. So if I switch that off, the capacitor now can be discharged quickly or slowly. I can discharge it very quickly by simply shorting it out, and you'll get a decent spark. If I try that again, I get a bit of a spark, not much of a spark there, but let's have another go. If I simply forget the switch, and just charge it up from the actual supply. If I whack that up to the full voltage, 24 volts, if I disconnect that, I should get a bit of a spark. You can see that spark. Try it again. You can see that spark. It's quite quick. Charge it up again, big spark. Now if I charge it up again, but this time I use a resistance to discharge it slowly, like this light bulb for example, you'll see that it discharges slowly. There's the bulb gradually discharging the resistor. Okay, so the bulb goes down to 0. If I charge that up again and use a discharge resistor like this one here, I can discharge it without any sparks. So this resistor is discharging it very slowly across the supply, across the capacitor. So if I charge that up again, get it the right way around, discharge it there. If I was to measure the voltage across there, I might be able to see the voltage decay as the resistor discharges the voltage. You can actually see the voltage on the capacitor decay slowly down to 0. And that's how you would normally plot the decay curve, by timing it every few seconds and making a note of that voltage, and you'd get the discharge curve down to 0. It's down to 1 volt now, it's less than 1 volt, and eventually goes to 0. So in your industry, capacitors tend to be used for what we call power factor correction. And power factor correction, the capacitors are very large, and physically large, and they're also charged up to high voltage, and you need the discharge resistors to actually discharge them safely without giving you a nasty electric shock or burns. Permanent magnetic fields, you have a bar magnet like that north to south. The magnetic field tends to take this shape. Like that. And the convention is for the magnetic fields to travel from north to south, like that. You can get a similar effect in an electromagnet. An electromagnet is a winding of copper wire around like that. And here the wire is going into the page. You could have something a bit similar. Something I've got a pen here. So I've got a pen. So if I get a piece of wire like this and wind it in a direction like that, if the current is going through the coil like this, it's effectively going into the page. So the magnetic field it produces is like that. And they all add up like that and produce an overall magnetic field in the same sort of pattern as the permanent magnet. The difference with an electromagnet is, of course, when you disconnect the current going through here, if that was positive and that was negative, if you disconnect it, the magnetic field collapses. So this is made of soft iron. Permanent magnets are made of a harder magnetic material. And they will keep the magnetism permanently. But in electrical engineering we need coils that can be energized and de-energized very quickly, and that's using soft iron. Okay. On some of the bigger cables that you use in your industry, you'll find the conductor is sticking out like that. That might be made of copper or aluminium. The outer insulator will be here. I'm rushing this a little bit because I'm running out of time on this second video. And there'll be a magnetic shield here. And this magnetic shield is to reduce the effect of these magnetic fields leaving the cable. So it's to keep the magnetic field inside the cable. So you might see that on one of the questions where you get asking you what this is. And this is a magnetic shield. Okay. Now some of the transformers that we've looked at have been double wound like this, but some of them are actually wound on a donut shape like that, where you have the windings around the outside like that, and you have might be another winding here going around there, and that is known as a ring transformer, or TX as I call it. Okay. And we know the losses are copper losses and iron losses. Laminations are usually used to reduce eddy currents, which are effectively an iron loss, because they are in the core. The heat loss in the windings is known what we call as power losses or copper losses or I²R losses. So there are two groups of losses. Okay, so I'll put an MS quiz on there, so have a go at that. Thanks very much.